Okay, thanks a lot for the introduction. It's very nice to be here. And I was assigned to talk about to review the status of the research in concerning the ISM in other galaxies, an extragalactic perspective on this huge subject. Of course, it goes without saying that I will take a very personal perspective on this. This is not going to be a comprehensive review of everything that has been done. Obviously, there will be highlights that are from some surveys or some projects and not others. So I apologize already if I'm not covering everything you would expect. But please feel free to interrupt as we've done in this series of lectures, and in general to contact me if you have any questions also after the lectures. I would also like to acknowledge contribution to the process that went into the building up these slides and this lecture. A lot of people that have been discussing this and discussing with or working with contributing in some form to this lecture. In particular, J.K. Hodge had a very a beautiful review talks on high redshift studies, and I took a lot of the inspiration from this for this lecture from her works. But then a lot of other people are included here contributed with many discussions, and a lot of material was also taken from the work that were presented in the in the ALMA conference we had last year, where we reviewed the status of the ISM studies in extragalactic environments. So that was very convenient, made a very easy platform for me to prepare this lesson. Of course, when we talk about the interstellar medium, we've seen the exquisite detail and the beautiful physics we can do in the local in our galaxies, studying clouds and star formation in our galaxy. Why should we go and do this job in other galaxies? Of course, we lose in angular resolution and in sensitivities. So a lot of the information that we can access in our galaxies will not be available for even the closest galaxies. On the other hand, we win in three main aspects, I would say, and they're labeled here as diversity, context, and look-back time. Diversity means that we can study different type of galaxies. For instance, we can see what are the properties of the ISM in AGN environment and starburst, but also in very low metallicity galaxies, and see what is different in these environments compared to what we see in the Milky Way. Another big advantage is context, and by this I mean that having an outside perspective on the ISM allows us to understand better where the clouds are and what is the general property of what are the general properties of the galaxies where the clouds reside, and this will be very clear later when we talk about result studies of molecular gas emission in other galaxies. And finally, the most obvious advantage is that we, especially when we start to do high ratio stuff, we go to very big distances, so we take advantage of the look back time to see how galaxies were and see what is the impact of the ISM in the evolution of galaxies. Having to find a starting point for the lectures, I think probably the best starting point is this paper by Ricard et al. From 1975, where it was announced the first detection of carbon monoxide in other galaxies, so beyond the Milky Way. This was found in NGC 253 and M82. We will come back to these galaxies repeatedly in the first part of this lecture. And you can see this is a sentence from their introduction where they say the searches of CO emission until now have been unsuccessful. Later on, they write that the observed features were strong enough to be detected with less sensitive receivers than the one they used in this study. However, they were probably missed due to the fact that the lines were too broad for the bandwidth of the receivers back then. And this highlights the two big problems that the astronomy of the ISM in the early days had to face. From one side, the sensitivity, and the other side is the fact that you had very limited bandwidth. So you really needed to know exactly the precise redshift of the source, the precise frequency at which you expect the line, which was not trivial. And for instance, carbon, the famous ionized carbon line was the first observation came much later than expected because the predicted frequency of the line was slightly off, and the receivers were so narrow that they were missing it. So, and also if the line is very broad, it might fill all your spectral width, so you see a continuum basically, you don't see the real line. 1975 is also a convenient starting date because in that year, Ward et al. Announced the first detection of a fine structure line, in this case from our galaxy, from the cloud M17, I think in Orion. So it's a convenient point to start this lecture. As a general historical perspective, I will not go much into this, but just to give you a feeling, you can distinguish roughly, very roughly, three phases. First part that I labeled here as the early days until the 90s. Then late 80s and obviously in the 90s, there was the advent of a number of facilities operating with single dish observations, especially at millimeter wavelengths. Thinking about SCUBA, and thinking about the IRAM 30-meter telescope and many other facilities around the world. And then around the 2010 or so, the advent of the big step forward done by interferometry at millimeter radio wavelengths. And I will emphasize what kind of impact this had in the recent development of the ISM studies in extragalactic environments. Of course, we shouldn't forget that in the meantime, there was also there were also efforts from space. In particular, the two milestones were the Infrared Space Observatory in the early 1990s, and then obviously Herschel more recently. This has been partially covered in the previous lectures, but just to make sure that everybody's on the same page. If we want to study the neutral medium and the molecular gas, which kind of tracers can we rely on? So for the neutral medium, the obvious line is the 21 centimeter line from the hyperfine structure of neutral hydrogen. This has been very well, the capabilities of the 21 centimeter line have been very widely discussed. This is a map, old sky map of the Milky Way in blue and yellow. So you see the stellar emission from the Milky Way, and what you see in pink is the hydrogen gas associated with the so-called Magellanic Stream. So it's the trail of gas associated with the Magellanic Clouds, which are this. Let's see if I have the mouse. With these two white blobs, which are the large and the small Magellanic Clouds. Hydrogen can also be observed in absorption. Neutral hydrogen can be observed in absorption. The famous, the most obvious example is the Lyman alpha forest. Now I have I'm showing here the energy spectrum of the energy level of of the hydrogen atom. This is from any textbook, the Osterbrock and so on, but most of physics courses include a discussion of the structure of the hydrogen atom. So this should not become as a surprise to anybody in the audience. I list the energy of the levels in terms of actually an excitation temperature, so in units of Kelvin. And this is convenient, as we will see later, because it can be related easily to the actual temperature in case of Boltzmann equilibrium, if you think that some level could be populated by collisions. This was something that I think Claudia Ceccarelli discussed in her lecture, I think Monday or Tuesday morning. And you can immediately see here that even for the lowest transition, the Lyman alpha line, where the first excited level requires energies that are very high, in order of 100,000 Kelvin. So this is not going to be populated by collision. You need other processes, in particular photoionization or recombination. So I have a quick question for the audience, for the students, to make sure that you're not all sleeping already. So we always talk about the Lyman alpha forest, and does anybody know why we don't have an H alpha forest, or if we have an H alpha forest, and if not, why? Anyone dares to suggest an option? I don't see the faces and I don't hear anything, so I'm assuming everybody fell asleep.
I'm getting worried too, Roberto.
Okay. That was the... We're still pretty early in the lectures. We have still like 150 slides to go through. So then, okay, to speed up a little, the answer is that in order to have absorption of H alpha is here, right? You want to have this transition from the second level to the third level. So in order to have that, you need a lot of electrons populating this level. But electrons shouldn't stay here. The excitation by radiative process, so the emission of a line, in this case Lyman alpha, is happens on time scale in, I don't know, 10 to the minus 10, and 10 to the minus 10 seconds or so, right? It's extremely fast. So you de-excite immediately. So it's really hard to keep photons in these, electrons in this level. They will always fall down in the ground energy level. This is why you can capture and bring up electrons from the ground state up to higher levels, but it's very difficult to get it from an excited level. This is the reason why you don't have H alpha in absorption, or typically, especially in the ISM, you don't have H alpha in absorption. You can have it in emission because you might have electrons starting here and then stepping down the ladder, and then that's a normal process, the radiative de-excitation. But you don't have the absorption. Lyman alpha forest, the idea is that you absorb the hydrogen atom absorb a Lyman alpha photon, and that is clearly observed, for instance, on the spectrum of bright quasars. This is a quasar redshift, the spectrum of a quasar from Sloan at redshift 3.23. You see the broad Lyman alpha emission here of the quasar. You see the quasar continuum, and then you see that at the wavelength below the Lyman alpha, the redshifted Lyman alpha, you see all these absorption line. The blue line is the expected reconstructed spectrum of the quasar, and you see that all these features are not noise. They're all on the lower side of the spectrum, meaning that this is absorption with respect to the intrinsic spectrum of the quasar. And this is indeed Lyman alpha absorption at various redshifts. You also see that in this case in particular, there is a prominent absorption at a specific redshift. This is what is typically referred to as the damp Lyman alpha system. So this was for neutral hydrogen. How about molecular hydrogen? Again, I think Claudia the first day discussed this extensively. H2 is not, it's very inefficient as a radiator. It's observed in emission, in particular in EGN Tori. This is a spectrum taken from a paper by Paola Caselli. And it's a spectrum in the near infrared. You see a number of lines like the Pascal alpha from hydrogen, neutral hydrogen. And you see, if you look very carefully, you see some molecular hydrogen lines. But again, this is a problem of energy of the levels in order to excite H2 so that we can get it in emission. Then you need you populate excited levels in order to see the emission. You need high temperature. You need hundreds, possibly thousands of Kelvin. This is observed in the nuclear around the EGN, in the torus, in the molecular torus, but it's not the classical example of the cold ISM where stars form. So this is not very convenient as a tracer of the bulk of the molecular gas. You can use the same approach as we said for neutral hydrogen using the molecule in absorption. The unfortunate part here is that the H2 absorption lines are all in the rest frame UV. And therefore, when you observe them, you are digging into the Lyman alpha forest that we saw before. So it's really a very complex and degenerate system. Also, it doesn't help that usually the reservoir of neutral gas, so H1, is much more extended. So the cross section, in order to see absorption, you need to see your source against a background bright quasar or something. And the cross section for neutral hydrogen is much larger, so it's easier to observe it in absorption, while the reservoir of molecular hydrogen is typically more confined to the central part of the galaxy, so the cross section is lower, so it's also rarer. We've already seen during these lectures that the molecular, the most common tracer of molecular gas is the carbon monoxide molecule, CO. It's one of the most common molecules, and in this case, I'm showing a plot from a recent paper by Emily Saint-Onge and collaborators, where you see classical star formation rate versus stellar mass diagram for galaxies. And all the points you see are galaxies that they have observed in their molecular gas emission. The dots are upper limits in their CO detection. They are non-detections, and the color points are sources that they actually detect. And this gives you a feeling on how many galaxies now we have sampled in CO, in the local universe, over a wide range of parameters in terms of stellar mass and star formation rate. There are also other lines. There are dense gas tracers, like HCN and HNC. We've already touched upon this during these classes. One of the advantages of observing these lines is that they're less common, especially if you look at the isotopology like C18O or 13CO. They have basically the same radiative structure as CO, 12CO, but they are much rarer, so you need a much higher column density in order to hit optical depth limitations. So we've seen that CO becomes basically opaque very easily at very low column densities, and then therefore you only see the surface of the clouds. These tracers allow you to go much deeper into the clouds. The other convenient part of this is that typically they have these lines, HCN and HNC and so on, they have higher critical densities, so the line emission survives the de-excitation via radiation, which produces the lines, survives even in high density environments, whereas the low JCO lines, for instance, would be depopulated by de-excited by collisions. This is an example from Meyer and collaborators from a recent study in NGC 253. These are spectra with ALMA, and first of all, you might notice on the very right part there is a CO line. It is completely out of scale in this plot. It's super bright, but then you see there's all this family of other lines. There's CN, CS, C17O, there was CO. So this gives a feeling of the rich chemistry that we can start to observe also in other galaxies. There are other molecules like water, OH, ammonia. Water is an interesting case. This is again the energy spectrum of the energy levels of the water lines in water vapor. As you probably know from your physics studies, the water has two different sets, can be para and ortho, two different sets of energy distribution. And again, once you plot these levels in terms of temperature, and you're thinking in terms of Boltzmann equilibrium, you can already tell that only the very low J transition can be populated via collisions. However, there are ways to populate the higher J levels. In particular, you can absorb photons at mid-infrared wavelength around 70 micron, and basically you have an absorption line associated with this transition from the 212 to the 321 and similar transitions, and this brings the energy, the electrons to a higher energy levels, and then they can decay radiatively. So you can see these transitions, the one marked in red as an emission line. This mechanism is known as infrared pumping, and this explains the fact that we do observe relatively intermediate and high J water transition even in distant galaxies. This is an example here shown from a paper by Rickers et al. 2013, where you see that the water line is basically as bright as a CO line. And this is exactly the same transition I marked in red in the spectrum. Finally, there are fine structure lines in the far infrared. Again, you must be familiar with similar plots. This is again the energy level. In this case, I showed two cases: the nitrogen, the singly ionized nitrogen atom on the left, and the doubly ionized oxygen. And the fine structure lines are basically arising from these transitions at the very low energy levels. And if you see the scale in energy, if you expressed again in Kelvin, we're talking about temperatures that are now very interesting if you think in terms of the cold ISM where stars are born. So this is very interesting because these lines can be easily populated. This level can be easily populated with collisions, and therefore they can be interesting tracers of this phase of the gas. Again, I have another question here for the audience, hoping that we will get a little more response this time. So you might notice that these two energy levels, the structure of the energy levels of these two species that I'm showing are remarkably similar. Okay, one is a little more stretched, but basically the transitions are the same. And Anyone dare to guess what is the reason of this difference? I mean, of this similarity, not this difference. Nope. So the answer is very, it's basically the answer is very simple. How many electrons does an oxygen, a doubly ionized oxygen atom have? If you think what is the atomic weight of oxygen is 8, you doubly ionize it, so it's 6 electrons. What is the atomic weight of nitrogen? That's 7, so you simply ionize it 6 electrons. And you wouldn't be surprised at this point if I tell you that the neutral carbon, which has an atomic weight of 6, so it will have 6 electrons. Atomic carbon is basically the same structure. So again, if you have two far infrared fine structure lines in the oxygen 3 and nitrogen 2, you expect two transition also for carbon 1, and that's exactly the case. So basically, the only thing that counts is the number of electrons for this. So this is just an example. M82 has been brought up earlier. I couldn't avoid showing this topical picture of M82 with its amazing outflow shown in red. And just to show that this is heavily studied in also in fine structure lines, I'm taking a few plots from Contursi where they show the map of oxygen 1 and carbon plus, and the velocity diagram based on only C plus, or the equivalent weight of oxygen 3 that highlights the base of the jet that is observed already in this fine structure line, not only in the nebular lines that produce the red halo in the left hand side image. So we have now touched upon a few different lines. In particular, I think you should emphasize C+. That's the line associated with the ionized carbon. This is particularly important because it's the main coolant of the cold ISM. This is demonstrated in the plot on the right. You see this is the cooling function that basically tells you where the gas is most effective in releasing its energy as radiation. And you can see that at the very high end, at high temperatures, basically the main vehicle to get rid of energy for a nebular for gas is synchrotron emission, free from protons and electrons, and then electrons. At temperatures around 10 to the 5 and 10 to 10 to the 7, emission lines associated with carbon, oxygen, and iron are particularly important. Then there is the strong contribution of the primordial elements, in particular the hydrogen. But then, as we say, the hydrogen becomes very ineffective as a radiator at low energies, and basically here at temperatures that are below, say, a few thousands, all of the cooling is done by basically two transitions: the ionized carbon, which is this mostly releasing this C+ line at 158 microns, and the oxygen line at 63 microns. And these are really the driver of the cooling of the gas at this temperature. Last but not least, of course, dust can be used as a tracer of the dense interstellar medium. Of course, we've already discussed that the dust is a catalyst, acts as a catalyst in the formation of the molecular gas. it has the observation an advantage that you just need a photometry measurement. You don't need to worry about not precisely knowing the redshift of your source. It's much cheaper in terms of telescope time to secure. Of course, then the drawback of observing dust is that it has a number of problems, like if you want to understand how much gas you have starting from dust observations, you will need a measurement of the temperature and other parameters that are not trivially derived from a single observation. But as a low order access point to the kind of interstellar medium information you can get for a distant galaxy, that's excellent. So if there are no questions on this introductory part, I will start with the discussion of the local universe. I was discussing with Jan, if you're okay, I will try to aim to have a break, let's say around in 1 hour or so, if that's okay, and we'll see a little how fast we go through the lectures. Again, if you are suffering too much, we can have different setups for the breaks. Any question? Any feedback? No? Okay, then studying the ISM in the local galaxies is a huge topic, and there was no way for me to make a comprehensive review of everything that's been done. So I decided to pick as a starting point the two surveys that came basically back to back in 2008. One is the THINKS survey. The acronym is questionable. It stands for the H1 Nearby Galaxy Survey. And it was a survey led by Fabian Walter using VLA at 21 centimeter, using the famous H1 hyperfine structure transition. And it imaged a suite of galaxies in the local universe at 6 arcsecond resolution. What you see here is a montage of all the maps they have put in the same angular scale, in the same physical scale of the galaxy, so corrected for their distance. And you see that they have a variety of sources, from very small galaxies and dwarfs to very big grand design spirals. The other survey, the companion survey, was the Heracles survey, that stands for Hera CO Line Extragalactic Survey, which was led by Adam Leroy and Frank Bigil, roughly in the same year. And basically what I did was to use the 30-meter, the IRAM 30-meter telescope to survey CO emission in basically the same sample of galaxies. You see here in this poster examples that they show the molecular gas from Heracles, the atomic gas from THINKS, the kinematic that they get from C1, in this case from H1, but also available from CO. And all these galaxies, have been pretty well studied. They have information on the whole stellar population from say Spitzer observations and optical and near-infrared data, and then they have a very good census of the star formation thanks to far infrared observation, far UV observation from galaxies, from mid-infrared tracers with the Spitzer, and then also some H-alpha observations. So they have all these components of the galaxy, and what they managed to put together was a substantial increment of our understanding of the Schmidt-Kennicat law. This is shown here in this plot. The Schmidt-Kennicat, or otherwise referred as the star formation law, shows the dependency of the star formation rate per unit area of a galaxy on the gas content in basically the amount of gas, the mass in gas in the same area. And you see here the color contours show the color scales shows the individual resolution element from Heracles and things. Then you have points that are parts of individual data sets from M51 and other resolved galaxies on kiloparsec scales. Then you have some global measurements for the very faint and low surface brightness galaxies that they don't have the signal enough to measure on a resolved basis, but they can detect while you integrate over the whole galaxy. And then especially for higher redshift sources, they take a global measurements of starburst, and these are these triangles that you should see here. So there's a lot to unpack from concerning this relation. First of all, it's fairly impressive to see in general in astrophysical context when you see a relation that stands over 3-4 orders of magnitude. And to first extent, you can say it's almost a linear slope. The diagonal lines are actually lines that you would expect if you had a perfectly linear relation. So, however, the fact that it's almost linear is not really completely true. And if you only focus on the neutral gas, the H1, you clearly see that you lose all the right-hand part of the plot. So the high density, high surface density gas distribution is missed by neutral gas. Neutral gas kind of saturates around this value that is around, say, 10 solar masses per parsec square. And basically the relation steepens and becomes basically a non-dependency, right? When you are around here, in terms of gas surface density, you might have a relatively low star formation rate or relatively high. On the contrary, when you look only at the molecular gas, the relation appears much more linear and robust over a wide range of surface densities. I haven't put it here, but the more recent work have extended this into this regime, basically using stacking and using correcting for the general velocity profile of galaxies and trying to map the CO emission at the very extended at the very end of at the very outskirts of the galaxies. And it seems like the relation is very linear through at least 2 or 3 orders of magnitude. So molecular and neutral gas tell two different stories. There seemed to be a transition, and this transition has been modeled in different ways. I will not go through the details, but there are various recipes that are used to make to explain the transition between the two regimes. And these recipes are typically what happens under the hood when you have a semi-analytical model or even a numerical simulation that tries to compute what are the properties of the gaseous reservoir. Basically, they assume some of these formulae to understand how much gas is in one form or the other. Another thing I would like to stress is that so on the y-axis we have the star formation rate per unit area, and on the x-axis we have the gas. So you can imagine taking the ratio of the two, and this defines a star formation efficiency. This is rather improper way to use the word efficiency. It's not a typical efficiencies in physics are numbers that go between 0 and 1, and it's a pure number. In this case, this is not a pure number. It has the physical dimension of the inverse of a time, and it's basically telling you how fast the star formation process is consuming the gas reservoir. So a better definition of this is the inverse of this, of the star formation efficiency, which is usually referred to as the depletion time, which can be considered as the amount of time you have in order how long it will take for the galaxy to burn out the reservoir of gas if it continues at this the observed star formation rate. Of course, this don't take it too literally. This is an indicative time scale. It doesn't mean that the star formation rate will go exactly on at this rate for the rest of the life of the galaxy. You should think about this as you know, when your car tells you that they estimate how many kilometers you can still do with the tank, the gas you have in your tank. That's basically it. It's a guess, gives you an order of magnitude idea if you should consider stopping at the gas station or not rather soon, but it doesn't provide you a perfect number. Another thing that we'll come back to in the future is in this lecture is that hidden in this in the definition of the x-axis is an assumption on some conversion factors. In particular, as far as the molecular gas is concerned, we said we measure CO, but then we talk about mass in molecular gas, molecular hydrogen. And in order to pass from one to the other, you need to assume an alpha CO factor. That and the uncertainties in this can easily be a factor 4, and we'll come back to this and its implication later in the lecture. Another point I would like to raise is that this trend, the star formation law, is something that is extremely dear to everybody that study galaxy evolution, galaxy formation, modeling, but it's probably not as exciting for someone working in our galaxy, in studies of our galaxies. And the reason is that giant molecular clouds don't follow the relation. They are scattered all over the place. This ellipse tries to capture what I remember from some talks, but they are spread all over this, a wide range in terms of gas density and star formation rate. The reason why this is working and you have this nice linear scale is probably something to do with some aerial average. Remember that these observations were based on single dish observations for, as far as the CO emission is concerned, and that means that the resolution was typically of 1 or 2 kiloparsecs in these galaxies, which means that you are averaging over a relatively large area where you have multiple clouds, and for instance, spiral galaxies, you might have spiral and inter-arm regimes getting all together mixed in your resolution in your resolution. So this probably contributes to the fact that what you see as a messy scatter plot for individual clouds becomes like an ordered, almost linear relation when you average over multiple regimes. Another, this has actually been exploited. For instance, there is a very interesting read from Croix and Longmore in 2014. They modeled the ISM as a combination of gas clouds and stars. And basically, they argue if you have a region of the galaxy where 80% of the time the gas stands as gas and then it's turned into stars, you can compute, you would expect something like this. You have a selection of clouds of gas shown here in orange and some stars or groups of stars that have been formed. And depending on whether your telescope is pointing on a star or on a gas cloud, you might have that the ratio between stars and gas changes. But of course, when you average over a relatively large area, then the two tends to converge to the average value. And their argument is that basically you can use the information of how quickly this converges and measure basically the lifetime of the gas clouds and some intrinsic properties of the star formation process. This is what they call the uncertainty principle, because formally it looks a bit like the equation of the uncertainty principle in quantum physics, but it's nothing to do with quantum. My last point on the Schmidt-Mechanical law, it's an interesting open question, is whether there is a maximum starbus. Is there a limit in terms of how many stars can be formed in a small region of a galaxy, provided you have sufficient material. And this comes from the fact that we have, especially in the very high redshift universe, we have examples of some quasarous galaxy or some SMG where you have really, really high star formation rates and in very compact regions. And it might be that these levels of star formation in such a small area might reach a limit, where basically it's some sort of Eddington kind of limitation, where basically you're creating so many stars that all this UV flux that these new stars will provide will blow away the rest of the gases reservoir, so it would saturate. It's an interesting concept that depends a lot on how you model the geometry of the system, but it has a sort of an application testable with observation currently. So going to a bit further with time, this was mostly based on works in the early 2000s and mid 2000s. Then of course Herschel came, and this was a huge leap in sampling the dust properties in local galaxies. I name here only two of the many surveys that were led with the Herschel. The Kingfish survey, it's a key set of nearby galaxies, far infrared survey with Herschel, and the Herschel Virgo cluster survey. So if you're familiar with the structure of the Virgo cluster, you have this map here is the whole Virgo cluster spanning somewhat like 15 degrees on sky in the vertical direction. And you see that basically they mapped with Herschel a huge area of this, including M87 and a number of other systems in this beautiful map that extends really over a huge fraction of the Virgo cluster. More recently, all the Herschel heritage has been taken upon from the Dustpedia project that basically compiled the observation of 875 galaxies with Herschel data, all in the local universe, redshift less than 0.01, and collected and reanalyzed in a self-consistent way a huge data set spanning basically all the optical, the far infrared, the far UV, the radio bands, This kind of homogeneous analysis is instrumental in order to bypass systematics in the assumptions, in the way that some technicalities are handled. I want to highlight here only a couple of results from a recent paper by Viana Casasola and collaborators. Here I'm showing the mass of molecular gas on the y-axis as a function of the dust mass. And you see that the dust and the molecular gas are pretty well correlated, as you would expect for the argument we raised before, the fact that dust is a catalyst for molecular gas formation. On the other hand, it's a bit more surprising that the atomic gas also shows a very good correlation with the dust mass in the same area, which is actually even better in terms of residual scatter than the one we showed before, and that the best correlation they find is with the total gas. So it seems like the dust doesn't really care for whether you're observing neutral or molecular gas. It's just tracing the total amount of gas that is available. Another beautiful and really impressive project concerning mapping the dust emission in other galaxies is the panchromatic Hubble Andromeda Treasury FET survey by Julian Del Canton and collaborators, where they spent somewhere close to 1,000 orbits of HST, and I say 1,000, to map a huge fraction of the Andromeda galaxy. The footprint is shown here in the image, and for comparison, they also added the size of the moon, just to give you a feeling of how big is the survey area. They imaged this region in multiple HST bands, and with that, they could reconstruct color magnitude diagrams on a star-by-star basis. So if you reconstruct the color magnitude diagram in a certain region where you assume the stellar age is similar, you have basically your Hertzsprung-Russell diagram, right? So you can get precise information of the intrinsic luminosity, the temperature of the stars, and so on. And with that, you also can understand the degree of obscuration, of reddening along that line of sight. And this provides you with an extinction map that has an impressive resolution, because you're averaging over a few stars, and you already get an information on the map, on the dust extinction. The power of angular resolution, I think, is really beautifully expressed by the pulse survey. This was the PDBI second Whirlpool Galaxy survey. The image you see here is the HST image of this very famous galaxy. This was the map of CO available before the pulse survey. This was the single dish observation by Schuster et al. In 2007. You see the angular resolution basically maps over 500 parsecs, and you can clearly see the structure of the spiral arms in the galaxy. If you compare again with the HST image, you can map that again in the single dish data, but that is basically it. So the big step forward that the interferometry delivered is this kind of level of detail. This is the map obtained with the pulse survey. This is at our second resolution, so you have a resolution in terms of physical scale of 40 parsecs. That's approaching the size of individual molecular clouds. So you can actually count how many molecular clouds we have in M51, at least in the central part where they observed. This amounts for more than 1,000 giant molecular clouds. And it's interesting to count how much flux in CO is coming from molecular cloud. It's roughly half of the total flux, which is interesting, meaning that a lot of CO emission is coming from a more diffuse medium. And they also find that in different parts of the galaxies, the clouds have different properties. So now that you have this amazing level of detail of order of an arc second, you can compare this map with other maps that you have of M51. So first of all, we have here the CO emission shown as white contours on the top of an extinction map, basically just an I minus H color from HST images. And you see that there is an almost perfect match between extinction and molecular gas. Okay, that's not terribly surprising. It's reassuring, but not surprising. When you start to compare with the far infrared, with the far UV from galaxies, things start to become a little more interesting. So you see that in general, okay, we see star formation happening in the spiral arms and a bit here also, and in the central region. But there are also two obvious things. First of all, there is a sort of an offset between the regions where the star formation is occurring and the region where most of the gas emission is happening. And then there are parts of the spiral arms like this one and this one, where there is definitely a lot of CO emission, but there is little to no star formation. Okay, but we say that the CO seems to be associated with highly reddened parts of the galaxy, and far UV is definitely going to suffer from that. Well, we get the same conclusions if we look at the H alpha emission instead of the far UV, and even when we go to the 70 micron emission, we basically come to the same conclusions. Here we are basically we are observing at wavelengths that are sufficiently long, so the extinction shouldn't be a problem. And yet you see that you still have this offset between the regions that are more star forming and the region where most of the gas clouds here is. And then you have these areas here where you have a lot of gas and relatively no star formation. So what is happening here? You have gas, but you don't have star formation, which is counterintuitive if you think in terms of the mechanical law we were talking before. One of the nice things that this system has is that these galaxies in almost face on. We have a very good understanding of the mass distribution. This is a stellar mass map of the very core, and we also have the dynamics from CO. So the galaxy is almost face on, but not perfectly face on, so we can actually measure the rotation of the gas in the disk. And we can construct torque maps like the one shown here, and we can relate basically the torque that the gas is experiencing in different parts of the region. You see this structure here, this complex structure is due to the fact that we have a nuclear bar in the center of the galaxy and a more extended bar and of course the spiral arms. And this local overdensity create all these complex torque moments. What is interesting is that different parts of the galaxy seem to have different depletion times, and as we already mentioned, regions where you have a lot of gas and relatively no star formation, so very long depletion time, and regions where you have a lot of star formation and relatively modest amount of gas, so very short depletion times. And this can be now put into context with the dynamical properties of the clouds in the gas. of the galaxy. In particular, this is the streaming velocity and the cloud dispersion velocity. So this ratio is basically telling you if rotation is prevailing over the velocity dispersion of the gas. And it's interesting because you can relate these quantities, in particular the velocity dispersion, to a pressure. We've seen yesterday afternoon, I think, when we talked about the Jeans map mass and the collapse. Basically, the pressure goes with rho times the velocity dispersion squared, and if you extend the Jeans formalism, the Jeans formalism assumes you have a cloud, and around the cloud there's nothing, right? And we integrate up to the mass cloud in the formalism that we saw in the lecture yesterday. If you instead of integrating up to, if you instead of having the cloud in the void, you put an environment with a gas, with a pressure, you need to, the equation becomes a little more complicated, but it's still something that can be analytically managed even by myself, and definitely the bar is pretty low here. And what you conclude is the formalism that is usually referred to as the Bonner-Ebert mass, and you find that the mass, the minimum mass required for the gas collapse, the cloud collapse, is scaling as the inverse of the square root of the pressure. So for high pressure, high external pressure, the mass of the cloud, the minimum mass required for the collapse is small. So high pressure, high pressure, small mass, it means that it's easy to make the gas cloud collapse and form stars. High pressure, easy to make stars. And this can be now interpreted in this context with the different parameters that we observe. A way to maybe even visualize even better what is happening is if you take the structure of the galaxy, you divide the arm regions, that's highlighted here, these regions, you call them arms, where along the spiral arms, and then the interarm region is divided into the region that is preceding the spiral arms and the region that is following the spiral arms. And then you consider, for instance, when you are rotating here at this distance from the galaxy center, what you see is something like this, right? This is now radius versus azimuth. We are sitting on a gas cloud that is orbiting the spiral at the center of the galaxy at a fixed radius. And we cross an arm here of the spiral arm and another spiral arm here, and here is the two zones that we described. And very simply, you can count how many gas clouds we have in this zone compared to this one, and just counting how many basically survive as we move in this direction, we have a lifetime of the clouds. What is interesting is that we find star formation basically on this side of the spiral arms. And again, the reason has to do with the local dynamic of the clouds. So the clouds are moving through the arms. They accelerate because of the local overdensity of mass due to the spiral arm. So their velocity is maximum at the maximum where they're crossing the spiral arm. As soon as they pass the spiral arm, so they are in front of the spiral arm, the clouds slow down, and this is because the overdensity is now behind them. So they're slowed down. So the velocity, the shear velocity is lower. And what happens according to Bernoulli's principle? What happens when you lower the velocity? What happens to the pressure? Any guess?
Pressure increase.
Thanks. Pressure increase. And we say that the pressure increase You have a lower von Ebert mass, so it's easier to fragment and to collapse the clouds and make stars. So this is why, surprisingly, star formation is not occurring in the arms where the velocity is maximum, but it's just after the arms. And if you go back to the plots we saw here, right, this is what you see here. The clouds have crossed the spiral arm in this region. Now they have a lower von Ebert mass, and they collapse and form stars. So this is the power of observing, putting together ISM studies and galaxy dynamics. And this is really difficult to do in our galaxy because we don't have the complete picture of the dynamics because we are inside the galaxy. So the next generation, the obvious step up from POES was to do the same experiment on many more galaxies. And this became an ALMA large program called FANGS that targets 74 galaxies at 1 arc resolution. And on the top of the ALMA large program, there's a NOEMA effort. I think it's also a large program. And of course, a lot of ancillary data from HST, from VLT-MUSE, and many other observatories. A similar approach with understanding the torques and how the dynamics relate with the gas motion has been applied now for the study of the feeding of nuclear starburst and AGN. Very briefly, we know that most of the massive galaxies have a massive black hole at their center, and many of these massive black holes at some point in their life are active. So you need to fuel their activity by getting gas to fall onto the black hole. This is not a trivial job because if the gas is just simply orbiting, you would expect relatively little motion, radial motion. So a big question has always been how to feed this AGN at the center. And now that we have the angular resolution to do this kind of studies, we can take observation of the CO as shown here from the NUGA survey from François Combs and Santiago Garcia-Burillo and many others. This is our observation of local Seyfert galaxies, and you can then look in details in the very center. And for instance, in this case, they observed the molecular torus around the AGN. This was a CO map. This is mapped now in HCO+. And first of all, I found really spectacular the fact that now we can actually resolve and map the AGN tori of, in nearby sources. The AGN community has been always assuming that everything is unresolvable and it's all point-like, but now that's no longer true, and it's really fascinating. One of the interesting results, and it's highlighted in this case, is that the dynamic of the torus doesn't necessarily go with the dynamic of the general galaxy disk. In particular, you can see here that the velocity gradient is mostly in this diagonal direction, while the torus is rotating in a completely different direction, right? So this is also interesting and has to do with it's telling us a lot about the history of accretion of gas and how this mechanism influence how the general structure of the galaxy and the merger history or the presence of spirals or bars influence the motion of stars and gas in the center, and therefore the accretion of gas. When you start to look into detailed maps of the gas in the center of galaxy, you might end up finding something weird, something you can't obviously explain with gas dynamics. And this is a clear example. Well, not so clear example maybe, but the observation of some gas clouds that are basically residuals from the when you remove all the large-scale disk component in the Circinus galaxy. Circinus is Seyfert galaxy. It's probably the closest Seyfert galaxy, and you have a prominent outflow observed in the nebular lines, the optical. And when you start to look in detail at the gas phase, this is again CO observations. You see this cloud here, this circled, and it's observed in many velocity channels. This is clearly a real feature. It's not noise or something, and it's completely inconsistent with the general rotation pattern of the galaxy. And it's well matched, well aligned on the top of the outflow feature that you see in the nebular lines. The interesting part here is that you're moving not just the ionized gas that is traced by the nebular lines, but you're moving molecular gas. It's a cold cloud here that is pushed out of the galaxy. It's interesting because you're attacking now the cold gas reservoir, which is the one used to form stars and to feed the AGN. The general enthusiasm and interest in understanding outflows in galaxies I'm saying this couple of slides for people who are not familiar with very obvious galaxy studies and galaxy formation questions. There are two main reasons. One came around the 2000 when people discovered that the black hole at the center of most massive galaxies has a tight correlation with some large-scale properties of the galaxies, in particular the stellar velocity dispersion is shown here in this plot from Gultekin, and the mass or the stellar light of the bulge of the galaxies. And the fact that this relation is in place and is so tight cannot be explained with simply, okay, big galaxies have bigger reservoir of everything. It's telling that there is some sort of coevolution between the black hole and the host galaxy, or some sort of interaction, some sort of feedback mechanism is enacted that regulates the growth of the black hole based on the properties of the galaxy, and vice versa. This led to the sketching of a number of evolutionary cartoons and concepts. This is one of them from Alexander and Hickox, where they take two gas-rich galaxies, they merge, they have what we call the wet merge with a lot of star formation, obscuration, and you have a classical SMG phenomenology. Then this can lead to an obscured, all this masked remnant of the merger might induce strong inflow of gas towards the center. This can feed the growth of the black hole, so you have an obscured quasar. Then the feedback from the quasar can get rid of the material, becomes an obscured quasar, and whatever is left is a gas that's deprived of its gas content, so it's becoming red and dead, and the fact that you messed up all the disk structure gives rise to the bulgy morphology. This obviously a concept. It's not. It's really hard to prove these scenarios. There are a number of clues and a lot of efforts to try to describe galaxy evolution within these schemes. Of course, it's always very difficult because you're observing different stages of. You don't observe the same object through its life. You observe different objects at different cosmic epochs, and you try to connect the dots. The other strong argument in favor of some sort of feedback mechanism is comes from the simple comparison of the mass function of dark matter halos, shown here in red. This comes from cosmology, basically from the lambda CDM. it's very solid in the sense that once you accept the lambda CDM model, there's not so much twiddling. The dark matter basically only follows gravity, so the description of its evolution is fairly simple. And you have this distribution that is almost like a power law. And then you have the galaxy stellar mass function, which is definitely not a power law. You have a power law part here, which is actually flatter than the one of dark matter, and then you have an exponential cutoff at high masses. So something is telling you that you need to decouple what the baryons are doing from what the dark matter is doing, in order to explain this, to start from here and end up with this shape. And what people have theorized is that there is feedback here and here. In particular, in the low mass end, the stellar feedback might be sufficient to blow away a lot of the reservoir of the gas, or at least to heat it so much that you delay the process of star formation, and therefore you end up with a lot of gas that is not producing stars. So you suppress formation of stars, and therefore you have less you lower the mass function here. At the high mass end, this process is no longer effective. This is because the potential well of the galaxy is so deep that it's very difficult to blow away the gas. You can heat it, you can delay a little, but on the long term, gravity will win anyway. So it's harder for stars to delay, to suppress the star formation. But what you have here is that you are in massive galaxies, and we saw that massive galaxies have black holes, which are probably active for certain parts of their life. So people are assuming that the AGN feedback is acting here to suppress the formation of extremely massive galaxies. Now, when we're talking about feedback, keep in mind that feedback can only act on gas. It cannot really do much to stars that have been already formed to first order. So basically what we are talking about is the role of the ISM in shaping the evolution of the galaxy. And this is why people have been studying in detail, looking for instance, for outflow from AGN. This is a compilation from a recent work from Dieter Lutz and collaborators, where they observed the CO outflows in local infrared luminous galaxies with an AGN, and they see there is an indication of some sort of I wouldn't say a correlation, but at least a trend with more massive outflows associated with the more luminous AGN. However, keep in mind that in these cases, this is the typical signature you have for outflows in the molecular regime. You have a very bright CO line that is the bulk of the molecular gas reservoir in the galaxy that is unaffected. And then you have a faint wing here, shown by this Gaussian, that is the one that is tracing, that is sensitive to the outflow, this part of the outflow. So first of all, in order to make these studies, you really need very high signal to noise. You can appreciate how difficult this game is to play in the local universe from this kind of plots. You can imagine how difficult it's going to be for high redshift, where the signal to noise limitation are even worse. And also the question is, okay, we are affecting the reservoir of gas. We're affecting some 10 to the 6 solar masses in the gas reservoir, out of a 10 to the 9 reservoir that we have. So we're affecting a very small component of the gas reservoir, and the question is, what is going to be the impact on the long term? And these are open questions. This is stuff that people are really investigating currently, and I don't think there is a clear answer in that. A better way, I mean, more unambiguous way to trace outflows is to use lines that are often observed in absorption, like the OH 119 micron line. OH comes as a doublet. You see here that this is the zero velocity is one of the two components, and this bar shows where the other component should be. And you see that in these two cases from a study from Rodrigo Herrera Camus, it's clear that the OH line is in absorption and blue shifted, which means that its material is with respect to the rest frame of the galaxy we're observing is coming towards us. So, and it's in between because it's in absorption, so it's an outflow. It's very obviously an outflow. Even more so if you see a P Cygni profile, like in these cases for other infrared bright sources from a study from Veilleux et al. 2013. The P Cygni is very unambiguously screaming of an outflow in fission. One last word on outflows. I find very impressive work that was presented at the conference last year here in Bologna, where Nico Krieger and collaborator presented this work on NGC 253, once again, one of the closest starburst galaxies, where they now have secured the ALMA imaging of the CO in different transitions. You see CO120 to 132 at an amazing resolution of 0.15 arcsecond. And again, after they removed all the pattern associated with the velocity, general large-scale velocity structure of the galaxy, they have some non-rotating components. These non-disk residuals are shown in the bottom panels here. And this again is identified as outflowing material. The nice thing is that when you compare this data with the 2 parsec resolution in another galaxy with the HST imaging at basically at the same resolution, you know where the star clusters that have been formed are. You see where the cloud is, and you see the offset. You see actually you can actually measure very precisely the location of the launching site and where the clouds are. And if you do some modeling of the stellar population, you can even have an estimate of the age of the star cluster, and therefore you can date when the outflow started, which, you know, it's mind-blowing. You can get all this information. You can actually reconstruct the motion of the clouds in a distant galaxy. I mean, it's a nearby galaxy, but still it's megaparsecs away, so it's really impressive. Maybe we could take a break here. What do you think? And then we go on with the rest of the discussion. We have some parts on we are roughly out the way. We have some discussion on multi-line diagnostics, and then we'll talk about higher redshift. So far, we mostly talked about one CO transition or so, and of course, many different lines have been observed in local galaxies. This is an example. Herschel was really instrumental here with huge spectral coverage, provided sampling of so many different transitions, in this case from CO4 to 3 to CO13 to 12. And on the top of that, some fine structure lines. In this case, we see the C1 here. Another CO transition is another C1 transition is here, basically attached with the CO726. Then you have N plus, and you also have some high density tracers. And when you combine all the information, I think Claudia probably mentioned this in their lectures. You can create what is usually referred to as the CO SLED, or spectral line energy distribution, and you see very different behaviors in the way that different transitions are emitted in CO. The Milky Way is in this case here with emission mostly in the very low J2, 3, and then basically nothing at very high J, and then as you go to other systems, in particular if you move from this galaxy to starburst early mergers and then AGN heating, provide excitation to higher and higher J transitions. And this seemed to be also related with the compactness of the emission, in particular diffuse systems like the typical spiral disks, in this case M51 again. You have that the emission of the CO is spread out over 4 kiloparsecs, and then you have mergers, early mergers, where you have the distribution of the emission is more kiloparsec scale. Merger remnants, advanced mergers are even more compact, with a lot of things happening only in half a kiloparsecs, like in ARP220. And then you can get to AGN and very intense central starbursts like MET2 or NGC 253, or in this case Markarian 231, which is which has a nuclear starburst and a quasar. And you have the CO emission is on a few hundred parsec scale. So the more compact is the emission, the higher is the concentration of the infrared luminosity, and the higher is the excitation of CO. These things seem all to go together and produce the very high excitation scenarios. Of course, once you have all these line diagnostics, you can try to model them and try to infer something about the physics of the gas. This I took this plot from Matilde's recent paper on local Seyfert galaxy, if I remember correctly, and she modeled all this transition, this sled of this system with the superposition of PDR component. PDRs are the photon dissociated region, where the excitation is driven by UV radiation from stars, an XTR component, where XTR stands for X-ray dominated region, and of course you need a source of X-ray radiation, in this case the AGN, and even a shock component. And as Antonio was hinting, you get contribution, especially at the very high J lines. And of course, these models are interesting because they give you some information on the density of the gas and on the strength of the incident radiation field. On the other hand, and also the root mechanism. If it's X-ray, so you think about AGN. If it's PDR, you are thinking about stars, star formation. But of course, this modeling is also very difficult because the multiple components can be very degenerate. There's also the fact that we are basically modeling, in most of the cases, we're modeling the CO sled with a limited number of clouds. In this case, basically these three components, and you associate each cloud to each component a certain density, a certain incident radiation field. Of course, you can imagine that in a galaxy, when you average over the whole galaxy, you have multiple components entering the scenario. You have contribution from different clouds with different properties. you can imagine certain parts where you are in the outskirts of the galaxy, the excitation is very low, so you mostly see only CO1 to 0 and CO2 to 1, and maybe more central regions where you have higher emission from also higher J transitions, and when you average all together, it's often difficult to have a comprehensive picture. So this is only a warning not to take these numbers, especially when you derive the density or the strength of the incident field, um, too literally, but as an indication. Um, Nature is usually very much more complex than we like to think, and but on the other hand, there is a lot of power in this approach, because then you do realize for instance, in this case, it's very obvious that stars are not enough to explain all the IJCO emissions, so you need extra component, you need excitation from other mechanisms. So I think this shows the power of this approach. Just keep in mind that our knowledge is this is a simplification of the real setting. This is only getting worse when we move this to high redshift, where we don't even have the spatial information to support us. There are other lines that have been studied, for instance, fine structure lines. This is a compilation by Tanio Diaz Santos and collaborators from the Shining project, where you see in each panel the oxygen 1 at 63 micron, the oxygen 3 at 88 micron, nitrogen 122 and 205, and the C plus at 158, divided by the infrared luminosity, and plotted as a function of the infrared surface density, so the surface brightness in terms of infrared luminosity. And you see that all these trends where the color code reflects the dust temperature, and you see that basically most of these ratios are pretty flat in the low surface brightness regimes, but then they drop at high surface densities. This is observed roughly in all of these fine structure lines. It's a bit more complex in the oxygen 3, which is way more scattered, while the trend is very tight, for instance, in C+. This is usually referred to as the line deficit. This definition is historical roots. It came from the early works with ISO in the 90s, where people saw that some galaxies, some ULIRCs were underluminous in C+, up to 2 decks below what you would expect, given their infrared luminosity. However, this definition is now outdated. One of the reasons is, as you see, it's no longer just a matter of C+. There are also other lines, although C++ is by far the most studied of these transitions. A few years ago, in 2015, we held a fine infrared fine structure line workshop in Heidelberg. I was co-chair with Karl Ferkinov. And in one of the discussion sessions, we came out with a list of possible explanation, potential physical causes of the C+ deficit. And you can see this. I'm not going to go through this list, but just to give you a feeling, it could go from self-absorption to contribution of the AGN to an infrared luminosity excess to compactness of the source and geometry, and for all these potential physical explanation, we discussed potential observables that we could test in order to see if this physical mechanism was actually in place or not. Very basically, for instance, if you are assuming that in some galaxies it's not that the C+ is underluminous, it's the infrared is pushed up, the infrared luminosity is boosted because, for instance, there's an AGN is providing a lot of UV fluxes and heating up the dust, so the emissivity of the dust goes to the roof, and you have, when you integrate over the acidity of the dust, you take um, the, if you raise the temperature because of the AGN, the power goes to the temperature to the fourth power, so you can easily get a much higher luminosity than you would expect. But if the AGN is the cause, then you should be able to see the AGN somehow in the sources. For instance, you can look at the X-rays, and hard X-rays should survive even in case of strong obscuration. So there are ways to dig into this phenomenology and see if the explanation holds. A visual representation and an example of how this kind of mechanism can be dissected is offered by this plot I took from a paper by Herrera Camus in 2018, where basically it shows that if you just play around with the geometry, you play in a case, the red case here, you assume that you take the dense PDR case where the OB stars that are providing the incident UV radiation are very closely associated with the clouds. And you end up with certain prediction in terms of C plus over far infrared luminosity as a function in this case of the infrared surface density. And in particular, you see that basically the luminosity of the C plus is roughly constant, and that the infrared luminosity is proportional to the input flux. On the other hand, if you scatter the clouds and you have a random distribution of stars and clouds, so you have a more distributed, spatially distributed system, then the infrared luminosity is again proportional to the incident flux, but in this case, the flux of the C plus is mostly dominated by the diffuse component, so basically it's mostly reflective of the density of the gas. And this results in very different behaviors in these plots, right? So this just to showcase how different physical description of the system can try to describe this C plus deficit. Why should we care all that much? One of the interesting parts is that C plus has been used as a star formation rate density. So we know that the infrared luminosity is powered in non-AGN galaxies. The infrared luminosity is powered by the extinction of the rest frame optical UV light. This is mostly due to young stars. So basically, the star formation component that is obscured by the dust is highlighted by the dust emission. On the other hand, the C plus traces both the mildly ionized medium that you have in H2 regions and the PDR surface. So it's both taking into account the PDR environment, the skin of clouds basically, and the more diffuse ionized medium. So could it be a tracer of the total star formation rate? People have investigated this. This is a couple of plots I took from the famous paper by Ilse Deleuze, 2014, where we show that the star formation rate here as a function of the C plus emission. Here on the left, it's on a spatially distributed scale, so each point is a resolution element in the galaxy. And on the right, it's the same plot, but now with global measurement. So each point is one galaxy. And you see that globally, there is an agreement, especially if you look only at the global measurements. There is a fairly nice relation between the star formation rate and the C plus luminosity. which would be tempting to use when you studied your high redshift galaxy and you only have C plus luminosity to play with. You can plug this into this relation and you get out a star formation rate. On the other hand, you need to be careful because then you see that again locally the environment can be very different. The ratio can lead can be very scattered depending on the system. Here, which is roughly in the middle of the parameter space, you might have for the same C plus emission, you might have more than a dex in terms of star formation rate, surface density. So, can we trust this conversion? It's difficult, right? Then okay, this concludes basically my overview on the lower local redshift. I will quickly go through the cosmic noon, which is basically in a very loose terms somewhere between redshift 1 and redshift 4. So the origin of this name comes from the fact that more than now around 20 years ago, people started, well, more 25 years ago, people have started to investigate the amount of star formation in a cosmological volume as a function of time. This resulted in the plot that is shown here. This is the famous Lilly-Maddow plot. And you have basically how many, this parameter that says how many stars are formed in a cosmological volume as a function of redshift or cosmic time. And you see basically you have 3 epochs. An early epoch, which is currently typically referred to as the cosmic dawn, where the star formation rate in a cosmological volume starts to grow slowly up to a peak. This is what we typically refer to as the cosmic noon, and then decay by like an order of magnitude down to the present age. This plot encapsulates the history of the star formation in the universe. In particular, cosmic noon, roughly half of the stars in the current universe were formed. You can see this in if you just plot how many stars, how much mass is in stars as a function of time, and the measurements and the fit is the measurements are the black crosses and the fit is the red line. And here I added also another line in orange, the dash line, which simply comes from integrating the previous plot. So this is how many stars you form per year in the cosmic volume. You can integrate as a function of time, and you should expect to see how many stars you got. And this is what you get. And you see that basically the integral from the star formation rate density overshoots the actual measurement. So questions to the audience. Anyone has an idea why we are overshooting? I guess I don't. There could be many causes, but anyone dares to?
Maybe this is due to a fraction of star formation rate that is obscured in the dust.
It's a good point. Unfortunately, that is probably not the answer, in the sense that at least up to redshift 3 or so, we up to here, we have a pretty good understanding of the dust thanks to Hersch and other surveys. So I don't think we will have much to play around with the dust. This is already corrected for dust emission, for dust obscuration. This is a very good point, especially the higher redshift.
Both these diagrams are based on observations, really?
Yes, yeah. Yes, and fairly independent observation, in the sense that one is summing the UV and the H alpha and infrared luminosity, and the other one is basically near infrared measurements, right? So just to give you a hint, I will show you just randomly this image The fact is that I don't know if that's just the answers.
Well, I was about to say
cycle.
feedback, but you.
Yeah, so part of the mass that is used in the formation of stars is returned to the ISM as stellar winds, but also supernova remnants and so on, right? So this fraction is usually called the return fraction, and this amount of gas can explain basically the offset in the two curves. On the other hand, I mean, again, if you think that the two curves comes from basically independent measurements, it's pretty impressive that the two match so well, right, over so many order of magnitude, so many cosmic, such a big part of the cosmic history. So we would like to understand what drives this evolution, this star formation rate density. Why? How come that galaxies at redshift 2 were forming 10 times more stars than what they're doing in the current universe? Because, well, we're talking about, we're in an ISM course, and we have learned that stars from the ISM, a very obvious question is it possible that it's the gas supply that changed as a function of cosmic time? So in principle, we would like to have a similar plot as the star formation rate density shown here, but now for gas, and see how much gas galaxies had in different cosmic epochs. And you can imagine a plot like this, where basically we are saying galaxies at redshift 2 were forming 10 times more stars because they had 10 times more gas that could be used for star formation. Or you can imagine a different scenario where the evolution is very different. And in this case, the fact that a galaxy at redshift 2 was forming more stars because for some reasons, geometry, morphology, mergers, it was more efficient in transforming gas. So it would, from the same amount of gas, it would be able to form 10 times more stars. Obviously, these are two extreme cases, but you can imagine a scenario where both these effects are in place and supply accounts only for a fraction of the evolution, and the rest is taken care of by the efficiency. So if you want to do it for this kind of measurement for H1, it's really tough to do it in emission. This is because the H1 line, as we saw, it's very faint. These are observations at redshift 0.1 from recent papers by Catinella and Cortese, 2015. And this is the Sloan universe, right? These are galaxies that are actually selected in Sloan. And you see in the top panel some of the brightest detections, and the lower panel some of the fainter detections. And you see, I mean, they know the redshift, they know where to look, but they're not the most mind-blowing detection on the market, right? It's really a tough game. And there's also a problem with artificial noise that becomes severe when you push at higher frequencies. The big expectation is for SKA, which will mark a huge step in sensitivity. So this will be this kind of research will be completely different when SKA will be online. Of course, we said before we can do the same game in absorption using the Lyman alpha line in the optical. I showed an example of the dump Lyman alpha system here in the plot that I'm repeating. The problem with the DLAs is that often it's difficult to find the counterpart. So you know there's a gas absorbing along the line of sight at a given redshift, but then you don't know which galaxy is responsible for that absorption. Now with MUSE, you can do IFU observations of a relatively big field and try to find which is the counterpart and find a number of galaxies in the field that might be at the same redshift as the absorption. But even in these cases, it's often complicated because sometimes you have more than one galaxy, and then who knows which is the one responsible for the obscuration. In some cases, this has been done also with ALMA. This is a plot I took from a paper by Emerson Neilman and collaborators, where you see basically in the top panels the C+ emission at the redshift of the absorber, and in the bottom panel the continuum. You see, for instance, in this case, you have the quasar is here, the absorption happens at this location because you use the background light of the quasar, but there is a C+ emitter here, and we're talking about a few arc-seconds across, so we are talking about, I don't know, 15 to 20 kiloparsec away, the galaxy. So basically, you are betting that the counterpart of the absorption is this C+ emitter. It's really tough to tell for sure. Usually it's easier when the source, the absorption is associated also with metal absorptions. We talked about the Lyman alpha from hydrogen, but you can also have absorption line from, say, magnesium or other elements in the spectrum of the quasar. And if you see these lines, you can infer the metallicity, and typically higher metallicity galaxies might have bright C+ emission, whereas if the galaxy has very low, the absorption system has very low metallicity, typically it's very hard to find the C+ emitter counterpart. That said, you can do this statistically and correct for how many line of, you take account for very different line of sights and infer how much H1 is available in the universe in different line of sight, and therefore reconstruct this plot where you have the amount of molecular, of neutral gas per cosmological volume as a function of redshift. And this is a compilation in the paper from Fabian Walter and collaborators. And you see that basically there's not so much of an evolution over a huge part of cosmic history from redshift 4 to redshift 0. It's basically flat, it's declining by a factor 2 or so, right? And this is very different from the star formation rate density plot that we saw before, where we had evolution by a factor 10. So H1 and star formation rate don't seem to be very correlated. What about the dust? Observing the dust at high redshift. Here there is what is often referred to as the magic of the millimeter. This is a plot of the LCD of a galaxy. We have the starlight emission and the synchrotron in the radio bands. You add some extinction. This is what is emerging from the galaxy, the starlight emission. Then you have molecular clouds and the cirrus. And this is the total SED of a galaxy. In this case, I'm taking the model of M51 and shifted at redshift 0.1. Just as reference, these are the typical observing band. You have from left to right, you have UV, the optical, near infrared in green, mid-infrared, far-infrared. The millimeter band is highlighted in red for reasons that we'll talk about in a moment, and the radio band is in gray. Now, what happens when we move this source at the same luminosity and we move it in redshift? So simply along the x-axis, you scale by 1 plus z. That's very simple. So you have a shift, a horizontal shift. We are in a log space here, so we're just shifting by a log 1 plus z. For f nu, so the y-axis, you shift up because of because we are using here a flux density. So it's this delta nu. You have the denominator that pushes the spectrum up. But then you have an increase in the luminosity distance, and that brings the spectrum down. So if you move from 0.1 as shown here to redshift 1, this is what you get. And I'm just to make the plot a little clearer, I'm just highlighting the millimeter band here and the optical band. And you see, of course, when you move from 0.1 to 1, everything is much dimmer, both in the optical and in the millimeter. Okay. So far, so good, but look what happened just after redshift 1. This is redshift 2, 3, 4, 5, 6, 7, 8, and even 9. So the optical band, basically, in the optical bands, basically the galaxy disappeared. This is not taking into account the fact that then above redshift 6, the galaxy becomes basically, all the flux becomes obscured because of the Gunn-Peterson effect. But even exactly the same SED is basically suppressed because you go down further down in this slope, right? And so the galaxy is extremely faint in the optical. But in the millimeter bands, well, at 1 millimeter, basically nothing changed. The galaxy is as bright as redshift 8 and 9 as it would be at redshift 1. And at 3 millimeter, it's even increasing. So the same galaxy would be brighter at 3 millimeter than, in terms of nu, right? In terms of flux density, it would be brighter than it would be than what you would get at redshift 1. And this is because of the negative K correction. Very basically, the shift in wavelength pushes you to closer and closer to the peak of the dust emission. So you're observing, instead of down in the Rayleigh jeans, you're now observing close to the peak of the dust emission, and that helps you and basically balances out the luminosity distance effect. So observing dust at high redshift is in principle pretty neat and convenient. On the top of that, you have other advantages, like the fact that the various CO lines are shifted in very easy bands. These are the red, orange, and yellow lines are the CO 120, 221, 322, 423, and so on. And what you see here is the observed frequency as a function of redshift, and basically you get all these CO lines that enter the millimeter range, where you have the 3 millimeter band is around 100 gigahertz, the 1 millimeter band is around here. So you see all these lines that are getting into the nice atmospheric bands of the millimeter astronomy. And on the top of that, you also have this fine structure line, the two C1 lines, C+, the two nitrogen line, oxygen 1, oxygen 3. And for comparison, this is what the VLA can observe, typical radio observatories. This is what NOEMA can observe in the 3 bands. And this is what ALMA can observe. So you have this amazing coverage of all these diagnostics that are now conveniently shifted into your observing windows at high redshift. In particular, the 3 millimeter is particularly well suited for scans where you want to get molecular scans, where you, if you manage to observe the whole 3 millimeter band, basically you get a complete redshift coverage with only a small gap between, say, 0.5 and 1. Of course, you need to take into account the atmosphere. This is particularly tough when you go to high frequency, above 400 gigahertz or so, and then 8, 9, 10 with ALMA. You see here, this is the transmission of the atmosphere as a function of frequency, and you see that as soon as the water vapor, the precipitated water vapor in the atmosphere raises above, let's say, 1 millimeter, you basically suppress all the transparency of the atmosphere at the high frequency. So observing in this regime is very tough, but it's still doable. This led to the advent of ALMA and other facilities pushed really the number of detection of CO in high redshift galaxies. This is a slightly updated version of the plot that appears in the review by Carilli and Walter in 2013, where you see the number of galaxies with a CO detection at redshift larger than 1 as a function of time. And you see that basically up to, say, 2010, almost the whole, everything we knew at this high redshift was done on some millimeter galaxies and quasars. And only in the last decade, we start to have a conspicuous amount of normal, say, main sequence or color selected galaxies that enter in this plot. I stopped updating this plot because really the there is this exponential growth, and it's really hard to catch up. It's also interesting to compare this with the advent of technological upgrades, like the advent of the WideX receiver on Plateau de Bure that expanded the simultaneous frequency coverage. This refers back to the opening paper of Riedek in 1975, right? Now we have spectral width, and then of course the advent of ALMA and the completion of ALMA in 2015 or so, that we reached cycle 3, and now we have all the antennas and so on. Just to give you a feeling, this was the distribution in terms of luminosity of the COM detection as a function of redshift. At the time of the review by, well, a little after, this was the year after the review from a paper I did. And just to give you a feeling of aspects, which is our molecular deep field in the UDF, now pushed down the typical lines are much fainter than what we knew a few years ago, right? So not only CO, oops, I should have changed the title of the slide, but not only CO, there are also fine structure lines. This was a plot that I did for the fine structure line workshop, and you see again this fast increase in the number of galaxies with fine structure line detection as function of time, and now this is increasing even faster thanks to ALMA. Typical galaxies, when we study galaxy high redshift, look like this. They're blobbish. We don't have all the detailed information on the morphology as we had for the local studies, but we have in many cases a very good understanding of their general LCD thanks to combination of multiple observation in the optical, often with HST, Spitzer, in this case even MIPS, Herschel, and then at millimeter wavelengths and possibly in the radio regime. We might have one or two lines that look like this. We can get very good constraints on general from the SED feeds of the star formation rates, star mass, and these parameters. There are different approaches to the study of normal galaxies at high redshift. Say where here high redshift means larger than 1. There are targeted studies, so you pre-select the galaxy because of certain properties, typically stellar mass and star formation rate. This was the approach followed by FIPS, by Alpine, and other surveys, and other individual studies. There are molecular deep fields I will talk about later. Clusters, so you, in order to maximize the efficiency, you observe a cluster where there's a lot of galaxies, of course, in your field of view, and of course it's a very peculiar phase of galaxy evolution, so it's very interesting to study them. In a single shot you can study many galaxies, it's convenient. You can capitalize on natural magnification from gravitational lenses. This is example, and I quoted an example by Desan Zavadsky and collaborators, but there are others. And of course, you can study the dust. And now there are a lot of surveys with the ALMA and other facilities that are investigating the counterparts of SMGs detected with single issue observations, like ALS, or just covering large areas in a big mosaic, let's say at 1 millimeter, 2 millimeter, at 850 micron in the UDF, in goods areas, so service areas where there is a lot of ancillary information with hundreds of orbits of HST time, and so very well understood, very well characterized multi-wavelength data sets on these fields, and you add the dust information. The obvious reference point here for molecular studies is the FIP survey, which is one of the largest. It's run by the Garching group, and they observed, they selected galaxies, main sequence galaxies, both at very low redshift, basically taking from the cold gas survey from Emily Santosh, the plot I showed at the beginning of the talk, but also at high redshift. Basically, they selected along this plot. This is again the star formation rate as a function of stellar mass of the galaxies. These are galaxies in the field. They selected in this box, basically at the top right. So they selected massive galaxies and with conspicuous star formation rates, and they follow them up in CO. Because of this selection, this was a very efficient strategy. They observed, they managed to secure a lot of detections. These are examples from the more massive part of the sample, stellar mass about 10 to the 11. You see very prominent CO emission in these galaxies. These are examples from the low mass end of the sample. And you see again a number of detections. Maybe the signal to noise in this case is not as compelling, but still you can get some order of magnitude estimate of the molecular gas reservoirs. These studies were really important because they allowed to put together the molecular gas content in high redshift galaxies with general properties of the galaxies. The way they did it was a bit convoluted, and I think it's depicted in this kind of plots where you see, for instance, the depletion time, which is something we've seen already. Basically the ratio between star formation rate, the ratio between the molecular gas mass and star formation rate. It tells us how long it will continue the star formation rate before we run out of fuel at the present rate. As a function of this quantity, which I will describe in a little, it's the specific star formation rate normalized by the specific star formation rate of a main sequence galaxy at that redshift and stellar mass. What that means is you have the stellar mass, the main sequence, so you have the star formation versus stellar mass plot that we started from. This is a combination of very different samples, but there is roughly a slope of 1-to-1 that shows the links, the star formation rate and stellar mass, and this is what is often referred to as the main sequence of star-forming galaxies. This is, if you take the ratio between the two quantities, star formation rate and stellar mass, you have the specific star formation rate, which tells you how many stars you're forming per unit mass. So it's a stellar mass, it's a star formation rate divided stellar mass. And this basically gives you the offset with respect to the red line. On the top of that, the star formation, the main sequence of galaxies seem to evolve as a function of redshift. So they correct for the star formation rate and the evolution of the main sequence and the position along the main sequence, and they get this axis. So it's very convoluted, but basically what this axis is saying in the horizontal axis here is how off you are from the main sequence. If you are forming way more stars than the typical galaxy, or we are forming way less stars of the typical galaxy. And what you see here for CO, and on the right, if you derive the amount of gas in the ISM from the dust emission, you see the same plot. They see this anti-correlation. So galaxies that are way above the main sequence have a very short depletion time, so they will burn their reservoir very fast, while galaxies that are below the main sequence do the opposite. This is not trivial because if you consider, for instance, the molecular gas fraction, so the molecular gas divided by the stellar mass, you have this behavior against the same plot again, and you see there are different trends. So if you separate in different redshift bins, you have a low redshift here and you have a high redshift bin. So you can clearly see that there is a trend at a given redshift between this offset and the gas fraction. So galaxies that are above the main sequence not only they burn their reservoir very fast, but they also have much more gas than typical galaxies on the main sequence. So they're very gas rich, but at the same time very intense, rapidly consuming this reservoir of gas. You also see this evolution in the gas content. So galaxy redshift 2 have higher gas fraction than the galaxies in the local universe. So basically, they are more gas rich. So this brings us back to the plots like this, where we have the star form. Here it's far infrared luminosity against the CO luminosity, and we can think about this as in terms of star formation versus molecular gas. So in a sense, this is an integrated version of the Schmidt chemical. Now each point is a galaxy, but we are talking about star formation versus molecular gas, so reservoir of gas. This is from the compilation from the review by Caselli and Walter, and you see that there is this sort of tight relation over 2 or 3 orders of magnitudes, and people have been discussing whether this is a single relation with a superlinear slope, or it's actually two relations with different two linear relations with a different intercept normalization. And one associated with the more normal main sequence galaxies. The gray points are here from local these galaxies, and the blue points here are main sequence galaxies from the Phipps survey. And then you have the starbursts that are on a higher level in this plot, right? On a different sequence. It's a bit academic to discuss to discriminate between the two, and I think there's no conclusive answer because it's a bit sterile discussion maybe. The question is, of course, if you again divide the x by the y, you get the star formation efficiency, or the depletion time going from the up down, from the top down, and you see that basically the argument for the two different sequences is that the main sequence galaxies and the local spirals tend to have a depletion time of the order of 10 to the 9, so roughly a gig a year, while starbursts that are up here have a much shorter depletion time, order 10 to the 7, 10 to the 8. And all the starbursts, quasars, SMGs at high redshift tend to populate this area. Of course, the big caveat here is that we've been through an alpha CO conversion, right? So we have measured the luminosity of CO. We want to have molecular gas, and we have to convert through an assumption of the alpha CO. And in the Milky Way, this is typically around 4 in these units, solar masses per Kelvin kilometer per second parsec square. But for ULIRCs and starburst, usually you get a value that is lower, around 1. So it's factor 4, and the factor 4 is roughly this long in this axis, right? And this would move, if you correct or not for alpha CO, you move basically all these orange and red points by this amount. So you basically move them back to the other to the linear slope of the disks. On the other hand, galaxies at very low metallicity, like the Small Magellanic Cloud, has an alpha CO of like 100 or 200, so it's way off this way, right, the opposite direction. It's very difficult to have CO observation of very low metallicity galaxies at a high redshift, because basically it's non-detection. It's very hard to measure that in the local universe, imagine at high redshift. But even just this factor 4 is very bothering. And a way to circumvent this is to get dynamical masses. Because if you have a dynamical mass, then you know what is the total mass budget, and you can compare with the luminosity of CO, and you say, okay, I know the total mass, I know the luminosity, I get a measurement of alpha CO. So it would be nice to have dynamical masses, precise dynamical masses of galaxies that you detect in CO. However, it's very difficult. You want to have velocity information, especially resolved velocity and possibly the velocity dispersion information. You need signal, very high signal to noise, and possibly you want different tracers, so you get different CO transitions or maybe some fine structure lines to compare things. The problem is that when you want to have resolution, we saw the beautiful maps of M51. M51 is a distance of 7 megaparsecs. So 1 arc second is roughly 35 parsecs. Redshift 4, this is the luminous distance, and 1 arc second is 200 times more. It's 7 kiloparsecs. So just to have a scale, this is 1 kiloparsec. If this one is 1 kiloparsec at the distance M51, this is 10 kiloparsecs at Redshift 4, and this roughly, it's not very precise because I don't have, I couldn't put the bar length exactly as I wanted, but roughly this is 1 kiloparsec at Redshift 4. So it's a factor 200 from here to this. So it's going to be really hard. There are a few lucky cases, and this is, I think, it's really showing how powerful is interferometry at radio millimeter wavelengths today. This compares the map of GN20, which is a 1 millimeter galaxy at Redshift 4, with the map of M51 from the single dish observations. Of course, I couldn't show the pose map, but the single dish observations are what we used to have for or the Schmidt-Koenig, the Heracles results that I showed at the beginning, right? And you can see now we have this amazing map. This is from the map of the SMGs from Hodge et al. 2012, and you see that we basically have the same kind of information of detail of angular resolution, right? Of course, we can do dynamics with this. This is the velocity map that we observe. You can model this, and in this case, for instance, you get an alpha CO of roughly 1, which suggests that we can't really move back the starburst to the main sequence relation. This case, this is just RGB image of this galaxy. This is the green map is the CO map that you saw before, the CO221, and I added here the dust map and the UV emission from the starlight emission for the same system. This is a nice system because then you could study the dynamics, get dynamical masses, do the resolved star formation law at Redshift 4, and get information on the clumpiness of the gas and the alpha CO. Of course, this is an extreme case. This is a very, very bright source. I think it's close to the 1013 solar luminosities in the infrared. And it took more than 100 hours with VLA to get that one map, which is fantastic. Really, it's one of my favorite maps, but it's not. You can't do that on big samples, right? You don't invest hundreds and hundreds of hours of VLA time. More commonly, you have to deal with marginally resolved maps, modest signal to noise, possibly one line. A typical situation, a high redshift. I don't want to demise the work of other studies, but this is what we typically do at high redshift. We have this particularly high redshift galaxy, redshift 7.2, and there is this detection of the oxygen 3 line. You can tell it's beautiful that you have something at the right frequency in the right place, but that's it. You can't do dynamics. You can't do much more than saying, okay, I have a detection. It's even hard to measure the flux in these cases, right? It's really at the limit of what you can do. Just to have a general feeling, dynamical tracers and general line tracers, you have for high redshift galaxies, you have in the optical, you have the Lyman alpha line is bright, but then you have other lines that are typically faint. In the optical near-infrared, you might have like helium or C+. These are nice, but typically faint and visible only for AGN, for bright type 1 quasars. The C3 line has been used in very high ratio sources, although again, it's very difficult to do dynamics because it's faint lines. In the mid-infrared, you have all the Balmer lines, the optical diagnostics there pushed in the near-infrared and mid-infrared regime, and they are now going to be accessible with James Webb. But currently, until James Webb launches, there's no way to do spectroscopy of these lines. In the sub-millimeter, of course, C+ is the brightest line. Oxygen, CO, other lines are also accessible, but they might be faint, and therefore it's going to be very difficult to do maps, resolve maps. Still, it's doable. This is C+ at redshift almost 7 in 2 galaxies from work by Renske Smith and collaborators, and you see that they have very nice detections of the lines, and then they follow them up and that some resolved information, and from this they had very rough indication of the dynamics. Of course, when we are talking about dynamics here, we are not talking about any detail. We are just saying order of magnitude. You need to assume tons of things. These are barely resolved, and you need to assume its rotation, what you see here, and that you have to assume an inclination angle and many other things, right? So it's uncertain. At least it will put you on a general order of magnitude estimate. We talked about following up detailed individual sources, but there's more. Molecular deep fields have been instrumental in covering uncovering the general budget of molecular gas. This is a rendering of the actual data cube that we got from the Aspexlar project, where we covered in a big mosaic, both in terms of aerial coverage and frequency, a huge part of the Hubble ultra deep field. And what you see here is actually these bright spots here are CO emitters in the cube. And one of the fascinating things is that by sampling just the whole field, we covered CO detection in galaxies that we didn't necessarily pre-select using the approach of Phipps, for instance. And it turned out that we had a big variety in properties. For instance, we have very broad and strong emission lines, but also very narrow lines in some cases, and in some cases probably a complex multi-peak structure. This is just to highlight the amazing, the beautiful images from Hubble of these galaxies, and you see you really appreciate the variety. You have these galaxies that are very red in this case, almost edge on, really edge on these galaxies. This galaxy is spiral, but it's rather quiescent. It's not forming many stars. You have larger than spirals. You have galaxies that you detect. You barely detect. This is a galaxy at redshift 2.7. You barely detect in the reddest near-infrared bands, and you don't see anything in the optical. And you see it only because this is the Hubble ultra deep field, and you have the deepest ancillary data on the market, and you can see something. Otherwise, it would have no counterpart. So you have all this beautiful variety of the properties, and really shows that the fact that you can't just if you want to have a census of the molecular emission at high redshift, you can't just rely on color selection of the more massive and star-forming galaxies. This is shown again, star formation rate versus stellar mass from the paper by Manuel Arvena and collaborators. And you see that we now detect CO even in galaxies that are formally below the main sequence. So these are galaxies that wouldn't be selected if you follow, for instance, the approach of Phipps. We'll get a very deep continuum map. This by collapsing our frequency scan at 1 millimeter. And this is the deepest observation of the sky in an extragalactic region at 1 millimeter available to date. and from simply counting the sources, we push the number count. This is the number of sources above a certain flux level as a function of the flux level in an area of the sky. And it's a compilation putting together the single dish work with SMGs and so on the right hand. And then here the black points are the aspects points. And you see that we cover this wide range. And in particular, you see this flattening at the faint end. And we're pushing in the territory that so far was explored only basically by observation of lensed fields. The problem with the observation in lens fields is that you do benefit from the magnification, but the magnification is uncertain if you don't know the mass model of the lens very well. And the part of the sky that is highly magnified is very small. So you will probably have very few galaxies entering that range, so you have larger Poissonian uncertainties. So before aspects, if you imagine to ignore the black points, there was the idea was that the number counts would keep on rising towards the faint end, and aspects clearly show that this is not the case, that there's a flattening of the count rates. And if you extrapolate this down, you get that basically all the infrared background from that you expect from Planck or so from CMB measurements at 1 millimeter is resolved in individual galaxies, and we know now each of these galaxies. We can not only know their redshift distribution, their mass distribution, the star formation rate. So we have all these sets of properties, and we can understand very well what is happening. The fact that we basically detected that there is this flattening is really flat means that even if you go much deeper in your observations, you're not going to gain much. You will gain 1 or 2 more galaxies even if you go a factor 4 deeper, and it's going to be excruciating. What is happening here is that the bulk of the dust emission is associated with faint galaxies the bulk of the dust emission is associated with galaxies in this regime that are 10 to the 10 solar masses, 10 to the 9 solar masses. When you go down in mass and star formation rate, you get to tiny galaxies who have very low metallicity and very low dust content, so they don't contribute any further to the population of the dust emitters. This is why there is this flattening. So going back to the sense of the molecular gas, this is now the same plot we saw before before we saw it for the neutral gas. Now we can see it for the molecular gas, and we see this plot. This is a result of a paper of mine and revised by the analysis in Balter et al. And now if we compare with the star formation rate density, we see there is a very good match. Now there are some systematics. I just shifted this to give you the feeling of the general shape, but you can tell now that things match very well. And so it seems like our question about which is the driver, if it's star formation rate, if it's the star formation efficiency or the gas supply, the answer is the cosmic star formation history is driven mostly by the content of molecular gas. At redshift 2, galaxies had 10 times more molecular gas, and therefore they were forming much more stars. Very briefly, we'll close with a small review on what is happening at the cosmic dawn, very extreme redshifts. If you're still awake, does anybody know how the temperature of the CMB scales with redshift?
Scales like 1 plus redshift.
Dear Antonio.
Yeah.
I would fire you if you didn't know this answer. I was hoping someone else. You're expected to know this. Anyway, so yes, it's scaling as 1 plus z, right? So if you take the CMB at redshift 6, it's 20 degrees, 19.1 Kelvin, right? And the Milky Way disk, the average temperature you get if you average over a large portion of the outer part of the disk of the Milky Way is around 18, let's say 15 to 20 K. Right, so it's very comparable, right? So what you would expect is that if you take a galaxy like the Milky Way and you move it in redshift and you go to higher and higher redshift, at some point the dust temperature will rise, not because of internal properties, but because it's heated by the CMB. So everything has to be warmer than the CMB, at least as warm as the CMB. So you will get this rise in the temperature of the dust emission just because of thermal equilibrium with the CMB. At the same time, the CMB acts as a background against which we are observing. What happens is that if you are observing the dust and the dust is basically the same temperature as the CMB, you will not be able to see this emission in a galaxy at high redshift. So it's true that it will be warmer, but it will be in equilibrium with the rest of the CMB temperature. So there's very little you hope to see anything. This is summarized by this plot, this analysis by very interesting paper by Elizabeth D'Acunha that shows in different ALMA bands. I believe this is starting from band 3 to band 10. I should have written, but basically you go to from low frequency to high frequency in the ALMA bands, and you see that the fraction of flux you would observe against the CMB decreases at high redshift. And basically at redshift, let's say 8 to 10, if you're observing 3 to 1 millimeter, basically you will not see the galaxy, the dust component of the galaxy. The same effect happens also for CO, and basically in this case, here we are assuming local thermal equilibrium. If the temperature is high, intrinsically is 100 K, there's very little effect. As you would expect, the CMB is 20 K, is still very low compared to the temperature of the gas. But if you are in this regime where the temperature is very low, then you basically lose a lot of the CO emission just because you're observing against a background that's as bright as what you are trying to observe. That said, C+ and other lines have been observed in high redshift. C+ being so bright, it becomes a very obvious workhorse to understand, to have a first insight of an extremely distant galaxy. In this case, it's a paper of mine in 2018 where we observed with only 10 minutes of integration with ALMA, we observed 27 quasars, and in 10 minutes we detected most of them, 85% of them. And you see, this is a testament of how sensitive is ALMA from one side, but also how easy it is to detect C+ emission in these systems. Since they are so bright, you can also push in angular resolution. This was a beautiful example from Brown-Feynman's published last year. This is the quasar-host galaxy observed in the C+ emission and underlying dust emission at 1.2 millimeters. And we pushed the angular resolution to 80 milliarc seconds, 76 milliarc seconds, I think it was. That's corresponding to 400 parsecs at the redshift of the quasar. And it's really fascinating, the quality of this map. I think it's really impressive if you think this is a redshift 6.6. The universe was, I don't know, 900 mega years old, and we have this quality of the information. I would like to spend a few minutes just to show a few examples. You can do the ratio between the C+ and the infrared luminosity and get study the line deficit on a resolved basis in a galaxy redshift 6.6. You can do a detailed analysis of the morphology. This is in the central channels around the zero velocity. You see there are these structures like sort of cavities that do not follow the expected rotation pattern of the overall rotation pattern of the system, It seems like there are cavities, and it will be interesting to understand what is going on here, possibly following up with other tracers. Also, the influence radius of the black hole, that is the area within which the black hole mass should be dominating the dynamics, is order of few hundred parsec if you assume that the velocity dispersion of the stars in the host galaxy is 300 kilometers per second, and that the black hole has 10 to the 9 solar masses, like in this case, which is comparable to what we observe here. However, we don't see a spike in the velocity dispersion of the gas in the center, and the reason is probably that in the central beam we still have some 10 to the 6 solar masses in C+, and with some reasonable assumption of the abundance, you can turn it into a gas mass, and this place is in the order of 10 to the 10. So you have 10 to the 10 solar masses of molecular gas in the central resolution element, in the central 400 parsec resolution element. And that's 10 times more than 11 times more than the mass of the black hole. So the reason why we don't see an imprint of the dynamic of the black hole is that there is so much gas there that it's still dominating the dynamics. Not only CO, not only C+. This is a compilation from a work I'm doing on ALMA observation of quasar-host galaxy, where we have CO 726 and C1 in a few cases. Of course, it's much harder than in C+, but we do see these lines in a number of quasars at redshift above 6. Antonio is working on a nice data set of water transitions in high redshift quasars. These are examples from his work, and you see we have multiple transition of the water lines in the system, so we can get some information on the powering mechanism of the ISM at these extreme redshifts. The most mind-blowing example of data set this redshift is still probably the SMG redshift 6.3 discovered by Riegers and collaborators, where you have here the Herschel spectra with a lot of follow-ups at different bands in the radian, the millimeter, some millimeter. You have CO, you have water, OH plus in absorption, C+, fine structure lines, really a beautiful data set. People have been also observing C+ in normal galaxies. This is examples from work by Stefano Carniani and collaborators. With in some cases they could have a good match with the counterparts in Lyman alpha and UV. Some cases there are potential offsets, like in these cases, or where probably the UV only tells a part of the story and the galaxy is more distributed. Some cases it's really confusing because you have an offset between the alleged line and the alleged counterpart, sorry, and it's not really clear if we're talking about the same source or not. So it's very complicated when you go to extreme systems like this. These are normal galaxy redshift 6 or 7, and they are really, this is HST resolution. They are barely detecting HST. It will be instrumental to see them with the James Webb, where we will be able to see the bulk of the stellar emission and see if this is associated with where the C+ is also, and the oxygen 3 line is emitted, or and maybe the UV only emerges here because it's the less obscured part of the galaxy. We will see. Alpine was a huge survey from the recent large program, and with a big commitment also from Bologna. It studied that it targeted the main sequence galaxy redshift 4.5 and 5 in C+, and this is their plot of the C+ versus star formation rate, and you see that there is a relation, although there is some scatter, and they use this to put constraints both from the dust and the C+ on the star formation density. And this is a very busy plot, but basically it's the sort of the Lilly-Maddow plot we saw before. We were looking at up to redshift 4 before, and now they're extending at higher redshift, where things are more debated because UV selection tends to go very far down, while infrared and radio observations seem to suggest that the drop might not be so fast. It's still highly debated whether the slope is so steep at higher redshift. I will I think I will, the last things I want to mention is that millimeter scans can be used to use ISM tracers to get redshift at these very high redshifts. This was used first of all with SMGs, which are bright, so it's easier. The problem was with SMGs that you have a resolution from single dish observation of 20 arcseconds, so it's very difficult to find the counterpart and then get the spectrum. So what people relied on was radio selection or optical counterparts, but then you lose the magic, right? You see something in the millimeter, but then you follow up in radio or in the optical and you see nothing, right? So it's very biased against galaxies at very high redshift. With the advent of ALMA, it was possible to do scans pretty efficiently. This was work by Axel Weiss and Guerra in 2013, where they observed a number of bright SMGs and detected a number of CO transitions that pinned down the redshift. And they indeed found that the early redshift distribution of SMGs, like the green histogram here, were biased toward the low redshift, while their work found the tail of the SMG population at the higher redshift. Scans are also used now for the redshift frontier. This is currently the highest redshift spectroscopic confirmation of a galaxy. With the redshift at 9.11, this is the brightest, the highest redshift line detected. It's C plus emission detected at, sorry, it's an oxygen 3 detected at redshift 9.1 by Hashimoto et al. And the perspective is the big project now is the Rebels project. It's a large program led by Richard Bowens and others. That will do scans to secure C+ and oxygen 3 emission in a number of galaxies, or UV selected galaxies, at very, very high redshift between 6.5 and 9, basically. As you see here, this is the selection of their sample. They have some techniques that show that this would work with some pilot programs that they did, and they indeed detected the lines in the redshift. This was what I showed at the beginning with the Rensky-Smith's velocity resolved maps. They plan to do this on, I think it's like 30 sources at redshift, really extreme redshift. And this will be really changing the picture of how we understand very, very, very high redshift galaxies from an ISM perspective. I think I'm done. That was everything I had.